All right, I'm going to try to shed a little bit of light on why this line is referred to as the least squares regression line. So here's our data set, which I have in this little folder here. And here's the regression analysis giving me the equation of the line. And then if I turn on this folder will be a visualization of the squares of the residuals. So if I open up this folder just to show you a little bit more. So those little lines there are the residuals. Those lines represent how far the individual data points are from the regression line. And then filling in the other four sides of that square, now we have a square. So these squares graphically represent the squared residuals or the squared errors. And the sum of the square of those errors is a little over 2,300. Okay? Then I have a folder where I allow the user to make the line wherever they want. So this purple line is I guess you would say, a user-defined line, and we can mess with the slope and mess with the y-intercept to try to find a perhaps better line than the least squares regression line. But also, we're going to have squares based on that user-defined line. So if I zoom in a little bit here, for example, this orange square is based off of the residual from this point to the least squares regression line, and this purple square is a square based on the residual from this point to the user-defined line. So we have orange squares from the least squares regression line, and we have purple squares from the user-defined line. And the sum of the squares of the residuals, or the sum of the squares of the errors, from our least squares regression line is 2308. The sum of the squares of the residuals from our user-defined line is 2661. And so if I try to play around with the y-intercept of my user-defined line, I don't think I'm going to get it under 2600. So I need to mess around with the slope a little bit. So now I got it down to 2800, and perhaps changing the y-intercept, I can get it down to 2400. Ooh, 2320. But notice that when I get the sum of the squared residuals, when I get that number really close to this number, it's because my user-defined line is very close to the actual least squares regression line. But anyways, the point is that it's called the least squares regression line because it's the line that minimizes the sum of the squares of the residuals. Now, even though I presented in the notes some formulas for figuring that out, those formulas can actually also be derived from calculus, because we can set up an equation that is the sum of the squared residuals and then find the minimum of those sum squared residuals by taking a derivative with respect to the intercept A and a derivative with respect to the slope B. But we're not going to get into the calculus of that. I just wanted to show you this visualization. So now on to one of the homework problems. Rubber powder has been used in asphalt to improve performance. So we've got y values that are axial strength and x values that are cube strength. And we're trying to see if there's a relationship between the cube strength and the axial strength. So here's our data, which is going to be randomized differently for different students. If we click on this Use Salt button, there's our data imported into Salt. Click on Regression, and for our explanatory variable, choose the x variable, and for the response, choose y. Then there is our regression line. Don't have to worry really about the confidence bands because we're not learning that this semester. And here's the regression equation. The intercept is negative 34.1833. Negative 34.1833, and the slope is 1.0133. So we got all the information we need there to get part A of this problem right. Part B is about the interpretation of the slope, which I covered in the notes. Or the second part of part A is about that. Part B is the coefficient of determination. So that should be on here somewhere. Here's correlation. And here's R squared. R squared is the coefficient of determination, so 6322, bam. And then it's asking us to interpret that. And then an estimate for the standard error, which is S, is right here, the residual standard error, 6.77. And also asking us to interpret that. So all of that is right at our fingertips by using SALT. Now, to show that in two other ways, I also took this data and put it on my calculator. So this is the same data from this problem. And I can do stat calculate linear regression. And there's our y-intercept of negative 34 and our slope of 1.01. R squared, 6322. And remember to get S from the calculator, instead of doing just regular linear regression, I would have to do a linear regression t-test on the calculator. And then I'll see a value of S, 6.77, which is what we're looking for there. So very easy to do that problem via technology. One more piece of technology. I have the data already entered in Excel. So I can click on Data Analysis, choose Regression. My Y values are in B1 through B11. My X values are in A1 through A11. I have labels. I want this to appear, the results to appear in D1. Bam. And again, there's our intercept of negative 34, our slope of 1.01, our regression S, 6.77, R squared, 0.632. So all of that stuff, whether you use Desmos, Excel, the graphing calculator, or the SALT statistical tool that's built in to WebAssign. On the second problem, it's even easier because the number crunching has already been done for us. So the constant is our y-intercept, and the coefficient of elevation is our slope. So you're literally just plugging the numbers in from this printout in the correct location here. So in this problem, our x-axis is elevation, and not only that, our x-axis is elevation in thousands of feet. So in this problem, every 1 unit increase in x is a 1,000-foot increase in elevation. How many fewer frost-free days are predicted? So this question here is just asking us about the slope, 30.34. And again, a question about coefficient of determination, question about how we find r from the value of r squared. That's pretty simple. The r squared is 946, so we take the square root of 946, but we have to write that 946 as a decimal instead of a percent, and we get 973, so that's our correlation, 9726. But notice when I take the square root here, it's always going to give me a positive answer, but correlation is sometimes negative. So how do we know if we want the negative answer or the positive answer? Well, the answer to that is the slope is negative. So if the slope is negative, the correlation is negative. So therefore, I'm taking the square root of r squared to get r, but I know I have to take the negative square root, so negative 0.97, because our slope is negative. And then here's a question on percent of variation. That's coming straight from the value of r squared. And if that percent is explained, then 100% minus that percent is unexplained. So pretty straightforward here, not much calculations to do whatsoever, because on this problem they've already done the number crunching for us.